What if you could completely replace an existing tool's logic while keeping its familiar interface? You'll see how to use a custom transform function to override a parent tool's behavior from scratch. The pattern takes full control of execution while maintaining the original tool's signature, letting you swap invalidation, formatting, or entirely new logic, all without breaking existing integrations.
Async def my custom logic, user input, SDR max length, int equals 100 SDR. Hash your custom logic here. This completely replaces the parent tool. Return F custom result for, user input max length. Tool, from tool, transform FN equals my custom logic.
This demonstrates the tool transformation pattern, a functional composition technique for adapting existing tools without rewriting them. The concept revolves around creating specialized variants of base tools by wrapping them with custom logic, argument mappings, or metadata overrides. What makes this distinctive is its non-destructive nature. The original tool remains intact, while transformed versions inherit and modify only what's needed. The approach works through declarative composition rather than inheritance. You define transformations as standalone functions or configuration objects that specify how to modify arguments, behavior, or metadata. The framework handles the plumbing, argument mapping, type validation, and execution flow, so your transformation logic stays focused on domain-specific concerns. This separation enables clean layering, where each transformation handles one responsibility, e.g., validation, renaming, or output formatting. This pattern solves the almost perfect tool problem, where existing functionality needs minor adjustments for a specific context. It eliminates boilerplate from writing wrapper classes or duplicating logic, while keeping transformations explicit and debuggable. Use it when adapting third-party tools, simplifying complex APIs for LLMs, or creating context-specific variants of generic operations. The trade-off is slight runtime overhead from indirection, but the clarity and maintainability gains outweigh this for most use cases. Let's break it down line by line.
Async def my custom logic, user input, SDR max length, int equals 100 SDR.
This defines an async function that implements custom tool logic, replacing the parent tool's behavior. The max length parameter with default value handles input truncation, preventing excessively long strings from causing issues downstream.
Hash your custom logic here. This completely replaces the parent tool. Return F custom result for, user input max length.
This implements the custom tool logic that completely overrides the parent tool's behavior. The slice operation, max length, enforces input length limits, preventing buffer overflow risks while maintaining predictable output size. The F-string formats the response in a standardized way, ensuring consistent output structure for downstream processing.
Tool, from tool, transform FN equals my custom logic.
This converts the custom function into a FastMCP tool using the factory pattern. The from tool class method wraps my custom logic in FastMCP's tool interface, exposing it to AI models while preserving the original function's signature and behavior. Tool transformation pattern. The transform FN parameter in FastMCP's tool from tool completely replaces parent tool logic while inheriting its schema, enabling radical behavior changes without breaking existing contracts. The function signature determines the new tool's schema, but the function's name and docstring are ignored during transformation. This pattern lets you wrap, validate, or extend tools without modifying their original implementations.
The tool that forgets its name answers to every name.